Okay, this is where we left. If you see here, the figure here shows the modulated carrier wave, or the waveform resulting from the amplitude modulation of a high frequency carrier wave by a signal that consists of a single audio frequency, say 5000 hertz or 5 kilohertz. So this is the modulated carrier wave that that is being produced or is resulting from an audio signal of frequency 5000 hertz. Let's just imagine that the frequency of the carrier wave is 50,000 hertz or 50 kilohertz, right? So this is the frequency, this is the time period of the carrier wave, and 1 over t of this value, 1 over t of this value would give you the 50,000, would give you the frequency of the carrier wave. Now, to find the audio frequency, you have to actually look at the waveform and find how many times it has been changed in a second. So, at the moment we are not looking at that. Let's actually change this graph to make it into a different domain. Let's change the time domain to a frequency domain. So we want to redraw this graph in terms of, rather than in terms of displacement time, we want to draw it in terms of amplitude versus frequency. I think we have done this before. If you remember, we had actually when we learned forced oscillation or resonance, we actually changed the displacement time graph where you had a damped oscillator, but actually we didn't draw a forced oscillator graph. But the damped oscillation, when applied an external frequency, we actually got an amplitude versus frequency curve, some sort like that, right? So amplitude versus frequency with the maximum amplitude occurring at resonant frequency. So similar to that, we are actually going to change this displacement time graph into an amplitude versus frequency graph. So what does this displacement time graph contain? It contains a carrier wave of frequency 50,000 hertz, and it will contain the information from the audio signal, and the audio frequency is 5000 hertz, right? So let's change this graph into an amplitude versus frequency graph. If you change this graph into an amplitude versus frequency graph, this is the graph that you will obtain. You will obtain the three vertical lines which are corresponding to three frequencies, right? The center line, which has the maximum amplitude, would be the carrier frequency, and then you have two other frequencies with called the sideband frequencies, which would be Fc plus Fa, frequency of the carrier wave plus frequency of the audio wave, and frequency of the carrier wave minus the frequency of the audio wave, right? So with the values that we had actually used, the carrier frequency was 50,000, so this would be actually 50 if I'm drawing in kilohertz. If the frequency is in kilohertz, that would be 50 kilohertz, and Fc plus Fa would be 50 plus 5 kilohertz, so it would be 55, and Fc minus Fa would be 45. Now it looks weird that this graph here could actually be converted into this graph, uh, where by just changing the domain into a, from the time domain to a frequency domain, you get graphed like this. It doesn't look very similar, right? It's actually done by a mathematical tool, right? I'll just give you a hint and a very crude example of how graphs can change when you do mathematical operations on them. Let's say you have a graph as such, right? Now there's a very simple way of actually changing this graph into that. Let's see. The graph is y equals to, say you have a y equals to x square graph, something similar to this, right? Y equals to x square graph, it may be x square plus something, but it's a quadratic graph, right? So it's a curve with a minimum point and as such. What mathematical function would actually change this graph into a straight line, right? So actually the mathematical function would be differentiating. So if I differentiate this graph, I'm going to get a 2x graph, y equals to 2x graph. This is a very crude example. It's not how the actual process happens, but you can see that curves can be converted into straight line graphs by mathematical operations of operations like differentiation. That's the easiest example I can find for you. So from this graph, if I want to convert to this graph, the mathematical transformation is actually called the Fourier transform. So if you ever do engineering, when you go a higher level, you're actually going to learn about the Fourier transform. And what the Fourier transform does is change things from the time domain into the frequency domain, or vice versa. It's actually a mathematical function. It involves an integral of a e power I 2 pi k and so on. So we don't want to know what's the mathematical function now, but we know that a Fourier transform would actually change a time domain graph into a frequency domain graph at the moment, right? So this is very important for you, because this is how all your images are actually converted, except for the case of scanning ultra microscope. If you take an X-ray X-ray diffraction spectrum, actually it's in the time domain, so only Fourier transform would actually give you how the picture looks like. So Fourier transform is actually very useful in observing image, and for analyzing. In your NMR spectrum, that's what actually happens. I think they're actually going to give you the curves in the peaks in a frequency domain, which is actually done by using a Fourier transform there, right? So for the moment, let's just accept that this graph, which is displacement versus time graph, when converted to an amplitude versus frequency graph, would contain these three lines. Now I used 5000 hertz as my audio frequency. Now nobody talks at 5000 hertz only. It will be just a sound like but we don't want that. Speech is actually containing a lot of frequencies. But let's say we have two frequencies, right? 5000 and 10,000 hertz. Uh, and 2000 two frequencies there. You have 5000 hertz and 10,000 hertz, right? Now what that would make is that would actually produce two more lines, which would be we're actually ignoring the multiples of FA there. So we'd actually produce at least two more lines, which would be 60 kilohertz and 50 kilohertz. So if you want to find the frequency of the sidebands, you just have to find, or the end parts of the sideband, you just have to find FC minus FA maximum audio frequency. And in this case, maximum audio frequency was 10,000. We had a mixture of 5,000 and 10,000. So the frequency of the sideband, maximum frequency in the amplitude versus frequency spectrum, would be FC minus FA max. In this case, it would be 60. Now if you see bandwidth there, bandwidth is actually the frequency range. So it's actually the largest frequency minus the smallest frequency. And in the first case, where we had only one audio frequency, the bandwidth is just going to be 55 minus 45, which is 10 kilohertz. If I had two audio frequencies, of 5 kilohertz and 10 kilohertz, then the bandwidth would be slightly larger. It would be 60 minus 50, which would, oh sorry, oh my mistake, I'm sorry, that would be actually 40, sorry. So the bandwidth would be actually 60 minus 40, which would be 20. Careful, would be 50 minus 10, which is 40. 50 minus 10 is 50. What am I doing? Okay, what we have here is the bandwidth. You can actually find the bandwidth using this formula as well, or this idea as well. It's twice the maximum audio frequency. If the maximum audio frequency is 5000 hertz, then the bandwidth is 10,000 hertz or 10 kilohertz. If the maximum audio frequency is 10 kilohertz, as you can see here, then the bandwidth is twice of that, which is 20 kilohertz, right? So you know how to find the amplitude versus frequency graph, and you know how to find bandwidth from that spectrum. As you saw, that's just remember that. So what we see here is a displacement time graph for not only one frequency. As you can see, the is this amplitude modulation still there? This is amplitude modulation still, because the frequency is kept constant, and is the amplitude that is being changed here, right? So if you see, the variation is all quite weird, right? It's going to be tough to analyze this. So what is normally done is displacement time graph which has got various audio frequencies, or continuous, a lot of audio frequencies, various audio frequencies, can be actually converted to amplitude versus frequency graph by a Fourier transform, right? So the amplitude versus frequency graph would look somewhat such, right? Amplitude versus frequency graph would look some sort as such. It's not necessary it should be curved there, but normally this is how the spectrum would look like. But you could also see the graph would be can be any sort like that. It should be symmetrical most of the time. Most of the time it should be smooth if you have all the audio frequencies. If you have certain frequencies that predominate in the in your speech, then those frequencies would actually peak here. So again, you can, if you want to find the bandwidth, they won't ask you from here to here. Bandwidth is still from the maximum till the minimum, right? So it's actually 2 times FA max. You would need to know how to convert a displacement time graph into an amplitude versus time graph, not by integration or not by Fourier transform, but you just analyzing the question and see how many frequencies are given. If one frequency is given, then you have 3 lines. If continuous or various frequencies are given, then you have a continuous region. It doesn't matter how you draw this, it can be of any shape, right? But as long as that would represent the bandwidth. Okay, I hope you understood that. I'll actually explain a few questions based on this, and at the moment that should be AM and FM for you, right? But continue reading in the booklet, because there are a lot of advantages and disadvantages for AM and FM. I may discuss that in class once you have read the application booklet. Thank you.